Deci, bună dimineața! Bine ați venit! Este un seminar general organizat în niște condiții mai deosebite, un seminar organizat în regim hibrid, cu prezență fizică și cu transmisie pe Zoom. Uite să mă și văd acolo. Invitatul de astăzi este dr. Grigore Moldovan, de la compania Point Electronic, GmbH. Înainte de a-i da cuvântul, am să fac o scurtă prezentare, am să dau citire unei scurte prezentări. Dat fiind că și prezentarea va fi în engleză și să nu mai încerc acum să traduc aici, voi citi prezentarea în limba engleză pe care o am. Grigore Moldovan is the Chief Technology Officer at Point Electronic GmbH, a supplier of electronics and software for electron microscopy. He manages technology, development, and marketing. Greg holds a PhD from University of Nottingham, has previously worked for Oxford Instruments, University of Oxford, and University of Cambridge. He is a scientist and a microscopist. Cu această scurtă prezentare am să dau cuvântul invitatului nostru, care ne va vorbi despre electrical analysis in electron microscopy. Vă rog.
Mulțumesc mult, mulțumesc foarte mult și pentru invitație. Este o plăcere deosebită să vin să vă vizitez. Îmi doresc de multă vreme să văd, am fost întârziat de pandemie, dar sunt încântat și abia aștept să aflu mai multe despre domeniul nostru de cercetare și proiecte de cercetare și despre ce urmărim. I will now switch to English. I hope you can all hear me. If you need to be louder, just let me know. And same online, if you can't hear me, maybe flag something up or send us a message. See what we can do about it. So I have prepared today material on one area of our company, electrical analysis. And I didn't really want to prepare sales slides. And I am technology, so I am developer driven. So I thought the best material to prepare would be one on technology, on techniques. What does this mean, electrical analysis? What techniques are used for it in SEM and TEM? And take a little bit more time than would have done otherwise and explain things, working up from simple to complex. I normally just tell everyone that I need to click on this PowerPoint. Now it works. Normally I just tell everyone that I am a CTO and that's my role, and I'm a scientist, I'm a microscopist, but today is special. I'm in Romania and I'm Romanian, so I decided I'd take a little bit more time to explain where I am and also to sort of explain why I'm here. So I'm originally from Țaraș. So for people that don't know, that if you go north and you go through Transylvania, through the other side, and just west of Maramureș, you'll find this little country, Țaraș. And it's probably the furthest out you can go from Bucharest and still find Romanians, sort of in a straight line. But that's where I'm from, on the border to Ukraine. And I have then done a physics degree in Cluj. And from there I went straight on with funding to the UK. And that was the point where I left, if you like, Romania, and I left the environment here. And I've been a foreigner ever since. And that's about 20 years ago. And I went to Nottingham, I did my PhD, and I stayed in the UK for a bit longer. I did a postdoc in Cambridge and another one in Oxford. And eventually switched to industry, which I like a lot more and fits me a lot better. And from the UK, then I moved to Germany and Romania. And that's a bit unusual. I'm kind of two locations at the same time. So my work is in Halle, and I have a team of developers there, and I do a lot of marketing as well. But I'm also spending a lot of time in Cluj. So I am spending more and more time in Romania. And I thought this would be the greatest opportunity to start to know your group as well and see what opportunities of collaborations we have. So when it comes to our company, Point Electronics, the supply of electronics and software, And the company has been running for about 30 years. It's quite well established in Germany and Europe-wide. It's a specialist in electronics, and electronics for all kinds of microscopes. And if we were to divide our product lines into several, I would say the first one would be custom electronics. If I could find my mouse. So by custom electronics, we mean one-of-a-kind systems, unique in some way. We've worked on special line sources, microscopes in multiple columns, positron microscopes, controlling and quadrupoles and octupoles and so on. And we like that a lot because then it's a great source of technology into the company. That means we can learn new things and we can develop new electronics, which we then take into systems that can be reused. I can take my mask off, can't I? So we can develop electronics we can reuse into other add-on systems. And by systems, we mean systems that we can add to existing microscopes or to new microscopes and so on for new techniques. And that was the case also for electrical analysis. Originally, it was a one-of-a-kind microscope many years ago. And then the electronics that we took out of that project came into a sort of turn-on key system for any STM or TEM. Electrical analysis is one of our sort of standalone systems. It deals with techniques like EBIC, EBAC, RCI, and this is what I'll be talking about today, and I'll go into great depth, but this is not our only field. We're very active in geometric analysis, and by geometrical analysis, I mean measuring things in 3 dimensions. So whether it's in true 3D or in 2D.5, as in surface topography, so 3D scanning as well, topographic reconstructions, and also correlative microscopy, so where you want to find the same location, different microscopes, maybe at different types, and so on, and also for archiving. And we do a lot of calibration in 2 and 3 dimensions, and so on. Another area that we're developing a lot at the moment is in situ microscopy. So this is where you work at high temperature, environmental gases, and so on in microscopes, particularly in STMs at the moment. When it comes to electron microscopy, over years, we've kind of grown into a range of techniques, and techniques is the best way to look at this and to understand how everything ties together. And that's why I like to focus on techniques. But these techniques actually go over a range of microscopes. So we work with SEM, and perhaps the ESM community is the most established one at the moment that deals with electrical analysis, but also with TEM, and TEM is a community that now is discovering these techniques and learning about more what is possible. And with the equipment that we work together with biasing holders manufacturers, we can turn that into a very simple system to install and use. And also in optical microscopy, so when we deal with optoelectronics, so there would be people working with LEDs, photodiodes, laser diodes, and so on. It's a great tool to use, but because sample preparation, it's easier and it's non-destructive. So we really go across several types of microscopes, and we go over many types of techniques. I have made a brief summary here, but actually today I'll be going through a majority of them on SEM and TEM. I will not focus on confocal scanning microscopy. So what is electrical analysis? Why do I use these words, and why do I mean by them? So historically in microscopy, the word microscopy, if you look back into the history of microscopy, comes from the desire to understand structure. And by default, that's what the word means. So understanding structure, measuring dimensions, seeing particles, interfaces in particular, defects, crystallographic defects, and so on. And another part of microscopy is microanalysis. So that means doing some chemistry on a very small scale and understanding down to atomic columns, the chemistry of interfaces, and so on. And now electrical analysis sits alongside those. That's the way I see it. And it is not dealing with structure, and it's not dealing with chemistry, it's dealing with electrical properties. So if you want to explore and you want to research into an electrical property at a nanoscale with an electron microscope, this is the technique. And it kind of bridges 2 other different areas. If you're a device scientist, then you would be very familiar with measuring curves, IV curves, CV curves, light-induced curves, and so on. And you would understand how the device behaves overall. So you would see the leakage current, the turn-on voltage, whatever that gains, whatever other things, maybe even an amplifier or transistor. It doesn't give a view of a microstructure, it just gives you a view of how the device behaves. And then we have at the other end the electron microscopy, which deals with structure and deals with chemistry. And what electrical analysis, it builds a bridge between these two things. So you can see electrical analysis at a nanoscale. So that's for a device, or the device specialist, somebody that is developing devices or doing fundamental research into devices. You will deal with this kind of research all the time. So you can see the IV curves, you can see the transistor curves, and you can characterize it. And if you know what it is a transistor, you can extract parameters from it. And you will be using an equipment like this, something that you can automatically run all the analysis you need. But for TEM, for example, there will be some examples here. I'm not showing micrographs, but what I show in black would be what you could see with a microscope. So you can see interfaces between PNN junctions. You can see interfaces to metals to get Schottky or Rubin contacts. You can see the overall structure. You can make cross sections and get high resolution information. What you cannot see, though, is where the electric fields are. You cannot see what the charge is doing. You cannot make a link to which defect in the material, for example, leads to a higher leakage current. And go around this loop is very important to get a good understanding of the device on nanoscale. So what I will be doing is I will slowly work up through techniques, and I'll start from very basic and very simple and go all the way to TEM. I thought that would be the best approach for somebody that's new to these techniques, but I will not do very advanced techniques. I will leave that for questions, or we can talk about that later. And perhaps the first technique, the most fundamental one that comes into this, and it's not a directly technique for electrical analysis, but it's a very good foundation, would be electron beam absorbed current. And it is exactly what it says. It's a current technique. So we measure the current absorbed into the sample. And that's the current that's due to the electron beam. So it's not light induced or it's not thermal induced. It's specifically, we mean the current induced by the electron beam. So that's the electron beam goes into the sample, gets absorbed. It's kind of a misnomer. It's not always true. We also have emitted electrons. In some conditions, you have mostly absorbed. In some conditions, you have mostly emitted. And I'll come back to that. But all these kind of things is referred to as EBAC, electron beam absorbed current. And it's not a new technique. It's from the origins of microscopy. It's maybe earlier than this reference. This is already in the book, so they must have been well known at the time in the 70s. And you have a good description of what this is, what equipment you need, how it works. And all we need is to measure this current coming from the sample, which we normally throw away into the touch alarm or the ground or something. But this time we will collect. So we will have a sample sitting on an SEM stub that is electrically connected to our amplifier or the current meter. And as an example, if we have a couple of particles, conductive particles on a substrate, it's also conductive. And really that is the only requirement, that everything is conductive, which we would be because otherwise you would charge. Then we get a current that is absorbed. So, for example, if that's our electron beam, then we will have backscattered electrons and secondary electrons, and we are really now referring to absorbed electrons, which historically has been defined in the old literature particularly as described as charge. So we are absorbing charge into the sample, and that forms a current which we then measure, as simple as that. So it's very simple, it's very straightforward, and that's why it's been discovered very early on, and it's very useful. If you develop instrumentation, but it's slow because the amplifier cannot be as fast as an in-lens detector or in-chamber detector. So kind of historically it's been put to one side and it's been overtaken by better detectors, faster detectors. But it will give us an image. What happens if we have an insulating material underneath a particle, for example, then of course the electrons absorbed in this particle cannot reach our substrates and we cannot collect it. So we will not get a signal. Of course, the electrons will accumulate, they will form a field, they will interact with the incoming electrons, they will produce image distortions and so on. So if we scan from left to right, we should see a signal when we have the beam directed to the substrate. This is the amount of current absorbed into the substrate. There will be some topography information because at the very edge of the particle we'll have secondary electrons produced and absorbed and so on, and the yield of SE and VSE changes. And when we have an isolated particles, we will read zero current. And this is an important aspect of the technique, is that we can say it's zero current. We don't say it's just black or it's dark. We can actually measure the current and we can say it's zero. So it's a quantitative technique in that sense because we know how much the signal is. So how do images look from EBAC? Well, it's the only requirement that it's conductive. It doesn't provide us with much information about electrical activity. And if we just take a standard sample for SEM, tin balls and carbon, then we would see pretty much the same kind of information as with the SE detectors. This is an in-chamber SE detector, and this is an in-lens detector, and this is EBAC image. And you see the SE detector, because it sits on the side in the chamber, it kind of pulls electron to one side, so we have this shadowing effect, which is great visually because it gives us a very good impression of 3D. Whereas the in-lens detector kind of looks straight onto the sample, so more like a passport type of photo. So if you like, in terms of illumination, like frontal illumination. And our EBAC is very much the same because there's no collection geometry. It's just beam going to the sample, current being absorbed. We don't have to worry about any other, where the detector sits in one. So this is EBAC. Another example is another standard sample is just thin gold nanoparticles in carbon. And the image is in pseudo color. We also know the relationship between color and current because we measure the current in every point. What I'm trying to show that in the nanoparticles, in the gold nanoparticle, we have orientation contrast. So orientation contrast shows not only on backscattered electrons, but it also shows in absorbed electrons because the current is all related. So current going in, current going out, the sum of all current. So all the signals are related. Another important point when we do these techniques based on electron beam currents is that it depends on density. And here I'm just measuring the percentage of the current absorbed into the sample as a function of material Z number. And of course, the lighter the material, the more current we absorb. The denser the material, the more electrons we backscatter, and we have less absorbed, and so on. So it's also a technique that we can use where the intensity of the signal depends on the material density. And then a final point about, and this applies to all the techniques that we're talking about today, is thickness. And particularly as we make the transition between SEM and TM later. So here we have a wedge of silicon. This is the thin wedge here. And we have quite a small angle, maybe a few degrees. So thickness is increasing as we're going from left to right. This is shown schematically here as well. And you will notice that where there's no signal, so that's our zero current is gray, and we have a region that's darker, and then we have a transition from dark to bright. And what is happening that when the sample is very thin, we have mostly emitted electrons. So the primary electrons go through the sample, they're not really absorbed in great proportion. They also excite more electrons. They move more electrons out of the sample, and therefore we lose overall electrons from the sample. So we extract the electrons from our circuitry. Whereas when the sample is thicker, then the absorption is dominant, so we have more absorption than emission. And if we plot EBAC signal as a function of thickness, which we can do because it's a wedge, then we can see there is a relationship between the two, and there is a saturation and so on. So that's EBAC. It's a very basic technique. It gives us the first introduction how all these current techniques work. The next level there would be RCI, resistance contrast imaging, and this is again another new technique developed a little bit later and kind of discovered accidentally by happy accident, I should say. And this comes from the failure analysis community. So these are failure analysts looking at why devices have failed and so on. This is more from the commercial end, but it's a very interesting technique and it's providing a lot of fundamental understanding about materials. How does this work? Well, this time we will have two connections. So not only one connection to the sample, but two. And we will rely on this absorbed current. So we have a thick sample, most of the electrons are absorbed, and we have a current absorbed that is pointed to the sample. And now we have two electrical connections. And we have resistance to each, of course. And the amount of current absorbed in each of the electrical connections, which are here nanocodes in this schematic, it's proportional to the resistance between where the current has been absorbed and the distance of the probe. So that means that when the electron beam is close to probe 1, then most of the current will come to probe 1. When the electron beam is close to probe 2, then most of the current will come in this probe and not to the other. So as we scan the probe from one side to the other, we will see the current going down. And if the material is uniform, we will see a constant gradient, so a constant decrease. If there are two grains, say, of different resistance, then we will see two different gradients. And from those, we can extract which one is higher, which one is lower, we can quantify resistance and so on. Most frequently it's used in a situation where we have a point of high resistance. So we have a low resistance, so gradient is very small, high resistance, but the gradient is very high, and another low resistance. So why is this interesting for failure analysts? Why are they using this technique? And this is for them the most frequently used technique, I would say, from electron microscopy. Well, it's because you can map resistance. So if you build resistance, for example, in circuitry, or if you want to understand where particular resistances are built in the circuit, then you can use this technique. And in this example, we have a meandering resistor built in a CMOS device. And you can see segments of this resistance, top layer, bottom layer, with a EBIRCH in between. And this is meandering along as a way of building up more resistance. So this way, you can design and you can make a resistance 100 ohms or 500 ohms or 1 kilo and so on, just by having longer chains or by having more layers connected through wires. And we can see how the intensity of we have one probe connecting at the beginning of this wire and one probe connected at the end of the wire. And we can see how the intensity of our RCI signal is going down as the resistance is building up. So it's a great technique to map resistance. You can go back and check, is my resistor uniform? Is it how uniform it is? And if it's not, which of the segment is not uniform? And then you can make a cross section and prepare TLM lambda. The most typical use is what the images that I'm showing here. You have a network, so we're looking down onto a CMOS chip. That's been unpackaged and delayed, so we can probe it with the electron beam. And we're looking down onto it, and we want to know how everything is connected. Say, for example, you discover in your device characterization that it doesn't turn on, a part of the chip doesn't turn on, for example, say. And then you know, okay, this line is not connecting power to the transistors that I need, but where this line is broken and why. And that's the problem that they need to fix. And we have two probes. We're doing RCI, resistance contrast imaging. One probe connected to this line, that's the line that is faulty, and another probe connected to the ground of the device. And now we have colored, but it's high intensity RCI signal in red, and we have overlaid it on top of ESC. So we can put everything in context, and we can see that this line is coming here, it's going through a wire, it's going underneath, to a deeper metal layer, and then coming up again, and then here it's suddenly disconnected. So it's a great technique to trace things, find where the failure is, and typically from here we'll continue with cross-sectioning with FIB to look from a side to see if it's a particle, contamination, or crack. What is it that has caused that failure? Another example is very similar, is shown here. Again, we have two probes, one to ground, one to these metal lines. And we know from the design that this should also be connected, and we can see that it isn't. So again, we have localized the failure, and we can continue. RCI is also used for different geometries, not necessarily left to right that I've shown. Maybe that's the easiest geometry to explain. Another geometry is we have an oxide to build a capacitor, or to build most typically would be a capacitor, so a thick oxide. And it could be between two metal layers, or it could be between a metal layer and a poly, and so on. And now we have the structure vertical. It's not sideways, it's vertical. And the way we do this is that we use the electron beam again to put the absorbed current just at the right depth, so they will be in the oxide. And then again, we split the current, but not sideways, we split it top and bottom. So some of the current will come to the top, some of the current will go to the bottom. And we want to find out at which points along this oxide there is a weakness, so the oxide is not as isolating as it should be, so there's a leakage path of some sort. If the material is perfect, then we should see a constant signal, so maybe some variations, as sometimes the oxide is not perfectly uniform in thickness and quality and so on. If there are two regions in this oxide, say very different capacitance or very different resistance or leakage across, then we would have quite a sharp transition. And if there is a leakage site, so position on the device where there is a high leakage current, then it will show us a spot. So if we build an image and the capacitor is this underneath this structure here, and there is one probe connected to the metal layer underneath, and there's another probe we can see here connected to the metal on the top, and we get a bright spot or where this leakages. And this example is using the electron microscope as a tool to localize things is even more important, because if you try and turn on this capacitor, it has a leakage, so it will produce a local melt zone, it will blow up. And once you have a melt zone, there is no chance of discovering what was there originally, what caused that melt. So this is a very great low power technique to localize weakness in oxides. Another technique in this family for electrical analysis would be electron beam induced resistance change. This is as a concept has been developed a long time ago, because it's an analog to optical beam induced resistance change. But it hasn't really taken off until now, and now it's becoming more popular, especially in the SEM community. It also applies to materials that work by changing resistance. Say if you have a memristor and so on. What is the principle of operation? Again, we have two probes, and we have a resistor, let's say, and it's an insulator, so we separate ourselves from the rest of the microscope electronics. But this time we will not rely on the absorbed current or into splitting the absorbed current as we did for RCI. This time we will force a voltage between these two probes. So we will force a current through the device. And we can control a bias, a voltage bias, and we can control the amount of current that we force through it. And this technique, we will use the electron beam as a way of changing local resistance. So if there is a weakness in a device, and let's keep that general, then the electron beam is sometimes able to change the local resistance of that weakness. And what it would happen is that as we keep a constant voltage across the probes, we would see a change in current because there's a change in resistance. So again, as you scan from left to right, if the material is perfect and is not responding to any changes in the electron beam, then we'll see no contrast. If there are grains that are sensitive to the electron beam, perhaps in different amounts, then we should see those grains in the image as well. And then if there is a spot, then that shows up in the image. And it's a technique used primarily for failure analysis at the moment. I think they are the first ones to really get into it and use it. And what it gives them is the ability to localize very precisely defects. So for example, we're looking at a transistor structure, and this transistor has been measured to have a high leakage. And the question, why does it have a high leakage? What is the defect? Is it in material, is it in fabrication, is it in the oxide or in the semiconductor? And we are forcing the current through this probe, and we're just changing how that current is changing because of the electron beam scanning. What is the physical origin of contrast? It could be temperature induced. It could be that some resistances on our device are sensitive to temperatures, and there is a small temperature difference because the electron beam could be. Another reason can be local electrical fields. So if we have two metal lines very close to each other, as we add a lot of charge because of the electron beam absorbed current, it's possible to change the local transport mechanism, and therefore you can change the resistance and so on. So it's the origin of contrast can be a very different nature, but the point is that you can localize weaknesses. So and it's primarily a technique for localization. So where the failure is, and then you would continue with TEM. Another technique, and it's perhaps one of the most popular ones in the research community, is EBIC, Electron Beam Induced Current. And again, this is not a new technique. Our contribution is not to develop the technique. Our contribution, like the other ones, is to provide all the electronics and the software for it, and all the training and application support and so on. And it's developed in the 70s. We see review papers, so it must have been very well developed beforehand. And this is a good review that goes into the theoretical aspects as well. It's a little bit more complex than the other techniques, so I will take more time to explain how it works. So this time we have our electron beam and it goes into the material, but we will not rely on the absorbed current. The absorbed current is always there, but we will not rely on that. What we will rely on is the induced current. And by induced current, we mean energy loss from the primary electrons. So they slow down through the material through inelastic loss. They transfer energy to electrons into to the material. And if the material has a band gap, and this is the main requirement, one of the main requirements for the technique to work, the material must have a band gap, then you would excite electrons on the valence ones or the conduction ones. So we will induce electron hole pairs. And that's why it's called an induced technique. So we don't rely on current from the primary beam, we rely on new current induced by the primary energy loss of the primary beam. And that happens always in a microscope when we have a semiconductor. Because it has a band gap. It also happens with ceramics. We also have a band gap. But so it always happens. Sometimes the electron hole pairs recombine to produce light, so there will be cathodoluminescence. Sometimes they recombine to produce X-rays, or they recombine to produce just heat. But most of the time, the information is not collected because they recombine very quickly. So they attract and they recombine and so. However, if there is a local electric field, and this is the second important requirement for the technique to work, if there is an internal electric field to the material, to the device, then the electron hole pairs are evidently separated. And they follow the electric field. And then they no longer recombine, and we have a chance to collect them. And just as we did before, we will use two probes, one connected to one side of the junction, say the P, and one connected to the N side of the junction. It doesn't have to be a junction, necessarily a PN junction, it could also be a Schottky contact between a metal and a semiconductor. So again, it's a current technique, induced current technique. It's used for the electron beam. It kind of falls within the same family of current or charge collection techniques. So as we scan the beam from left to right in our example, where we're very far away from the field, the electric field, we will get no signal because the electron hole pairs will recombine. As we come closer into the field, then some of the electron hole pairs will diffuse, will walk randomly, and some of them will get collected. And the closer we are to the electric field, the more we collect. So there will be an increasing edge. When we are inside the field, the majority of the electron hole pairs will be corrected, and we have a high current, and then go through the other side. So we get this kind of profiles where we have high current, where there is a field, and we have quite diffused edges around them. So it gives us an opportunity to map electric fields. We can see where they're on the device, but it also gives us an opportunity to understand and localize defects. So by defects and EBIC, this would be defects in the semiconductor. So we're talking primarily about dislocation, grain boundaries, stacking faults, and so on. Where we have a defect, let's say that the defect is in the middle of our field, then there will be a competition between separation of electron hole pairs due to the field and then recombination, non-radiative recombination. And therefore, we will start to lose some of the induced electrons and we will see a small signal. So we can see for defect it's active electrically. We can also see how active it is. We can measure the contrast of this signal, so how much signal we're losing because of the recombination. And also we can see a capture diameter, so how much around the dislocation is effective and so on. We can also see from the edges of these fields, we can pick up information on diffusion because all this profile is diffusion driven, and this is diffusion of minority carriers. So we can measure with high spatial resolution diffusion length of minority carriers. So it's quite a powerful technique, and it's been developed very extensively, and it's been used very heavily. I'm only going to scratch the surface a little bit. This is an example where you can map where the electric field is. We have some high power transistors. In the S imaging grade, we don't see the fields. We can only see the plugs that connect our junction to the rest of the circuitry. And once we use EBIC, then we can illuminate, and we actually overlay this red over the S image, and we can see where the field is. If you do device research, you can then go, is it where I meant it to be? Is it bigger? Is it smaller? You can interact with it. You can apply a bias. You can go to reverse bias and make it larger. You can go into forwards bias and make it smaller. And the same is for transistors. You can then apply on a gate a signal. You can turn it on, you can turn it off, and you can see how the fields react in different operation conditions. And this is an important topic, in situ topic for EBIC, is that you can interact with the device and you can see how it operates. It's done not only in plan view, it's also done in cross-section. And here we're looking at a CMOS device. We have the semiconductor, the silicon underneath. We have the oxide on top. And we can see some poly and metal tracks here. And this is the transistors. There's one connected to high, source to high, and drain to low. So we only see in this image one connected to high, and we can see the electric field associated with the doping for the source, let's say. There is another electric field which is used to isolate this transistor from the next. And this is the main reason to you do cross-section. When you have stacks of different fields, then you can separate them by looking on a cross-section. It's used not only on CMOS technologies, used when research is mostly used on new technology, on new devices. Say you're developing a new solar cell. This is a solar cell. And this has been textured for maximum light absorption, and it then has been implanted, and you just want to see how the implantation has worked out. What is the relationship between the implantation, the fields that result from this implantation, and topography? And you can do this in the SEM on a large scale, and you can find sites of interest, defects, and so on. Another example would be in fundamental research, looking at levels in the band gap of where the defects are. So at which temperature does this recombination center switch on and off? It's proportional to where they are in the band gap. And this is an example on a solar cell again, and it's textured, so that's why we see these pyramids. Remember, all the absorbed techniques, current-based technique, also you have information on topography and density and so on. But we also have here a foreign particle, and it shows as a shadow because it's thickness-driven as well. We know these are not induced current because the edges are very sharp, where for EBIC we also always expect diffuse edges because of minor charge carriers. And we know these are the defects, we can see them, and this is at 20 degrees, and if you go to 250 degrees, we see the contrast, so the amount of recombination of these defects is changing. And that is giving us information about level of these defects, and then we can start to associate them with what impurities or what could be the origin of that recombination. So that is EBIC. EBIC, it's a term used for SEM primarily, but is not only used in SEM, it's also used in TEM, and you'll find it up in different names. Perhaps the oldest names that I'm aware of is EBIC, Scanning Transmission Electron Beam Induced Current. And again, you see, not new techniques. We're not aimed to develop new techniques. There are more advanced techniques to talk about, but these basic techniques, they've all been around and very well established from a long time. Very similar, or the same principle, however, there's a major difference is that our sample is always, the sample is always thin. So that means the primary electrons, they're going through, they're becoming transmitted electrons. So we don't really have an absorbed signal so much, but we still have emitted electrons, which in these techniques, they tend to be called more recently secondary electron beam induced currents. But we are also losing electrons from the sample, again, function of thickness, function of density. Another interesting effect is that transmitted electrons are slightly deviated, or the angle is changed because of the field they're going through. And that can also be picked up with scanning with differential phase contrast. But I'm not going to go into that technique today. All we're going to do today is just, we're going to collect the current that goes through it. In terms of a EBIC curve, and it's the same whether it's SEM or TEM, the signal that we're collecting is this one on the EBIC curve. So we in the reverse direction, it could be a zero bias, or it could be a some bias, and that's the signal we pick up as we scan the beam. In cross-section, and TEM tends to be cross-section of thin lamellas, we will have a relatively constant signal where in the middle of the junction, so where the built-in field is, and we can change the width of this field by applying a bias, so reverse bias to widen it, forward bias to narrow it. That's the in situ part of the work. And then we have diffuse edges on either side. And again, we would be looking at how fast these edges are decaying to see what is the diffusion length. In TM, so this has been developed a long time ago, but it used to be very hard work. So you had to make your own holder, you had to figure out your own way of making connections, and so on. It is only recently that we have started to have biasing holders, and that makes the work very easy. You no longer have to spend half a year, maybe more, to build holders and make them mechanically accurate and so on. So whereas this technique used to be quite rare and done only in very few places in the world and 10 years apart, now it's becoming very immediate and very easy. You just connect everything up and you get the result on the same day. And it's easy not only because of the holder, but also because of a carrier that have started to be made. And this carrier chip has all the connection that you need in order to electrically connect the TM lamella, the fragile TM lamella, to some tracks and then to cables and so on. And a carrier chip from prototypes, for example, it would have an opening. I'm only showing a very small part of the carrier chip because it's a very small opening. You can barely see it with your eye. The lamella would be typically connected on two sides, left and right, and we would connect, in our image, this would show as top and bottom into the lamella. And those then are carried through the tracks, through the chip, through the holder, out into the electronics, so we can measure the small currents. So we see we have some signal. Again, this is a HALAF image in gray overlaid with EBIC image in red. And we see several things in this image. One of them is emitted electrons coming from this thick deposited connections. But we also see an additional signal that comes from inside the gallium arsenide lamella. So then that's the junction, the one that we're aiming for. So as an example of working through how this works, this is a known sample. Typically we work with nano sample, but this is a known test sample, just to figure out that everything works and what information we can extract with. And this is very great work done by Aidan, Rudy, and Sia Letty. We have a great collaboration with the people there. And this is an ST image, and you can see the lamella prepared by FIP. It was made relatively thick, extracted, connected then to the chip from chip carrier, and then finished as it's held. It's held here so that you get it down to electron transparency. It's a silicon PN junction, so we know what it is, and we know from the recipe of how this was made how deep then down the PN junction would be, so we know it's there. So if you then take this to TM and we do a HALAF signal, STEM image, then you can see more details, and you can also see that this has been prepared at different thicknesses as a test device. And we're going from something like 350 nanometers all the way up to 1 micron. So same material, same junction, different thicknesses. And again, we see some emitted electrons that come from the thicker parts. This is thicker, and also in here, it's thicker there, but here it also has higher density. So remember, all these current techniques have some thickness and topography signal contrast as well. Same at the bottom here. And then in addition to those, we also have another line here. And that is the PN junction. And you see as the thinner the lamella, the smaller the signal, because we have less material to lose energy and therefore less induced currents. As we have thicker materials, more current and also more diffusion. And more diffusion, is it more diffusion because it's thicker, or are there some other things at play? And we can extract line profiles going across these EBIC signal images, and we can extract, using the standard EBIC analysis, we can extract diffusion length of minority carriers. But to take that slowly, we see that the edges away from the field go all the way to something like 400 nanometers. So quite far away from the junction. If we compare that with some Monte Carlo simulations, how far we expect the electrons to deviate from their path as to go to thicker and thicker materials, we see that, yes, as the materials go thicker, you expect the primary electrons to have more displacement, but this is tens of nanometers, so it's about 10 times smaller than the diffusion-driven signal that we see here. So we can then apply a standard formula and extract the decay parameter from here. And then we can give with good confidence what the diffusion length of minority carriers is. And this is an important fundamental physical parameter, is diffusion length. And we can measure that with high resolution. And what this is showing us in this particular example is that as the lamella is becoming thicker, the diffusion is also longer. So that means the diffusion of charge carrier is not limited only by purity and the doping of the material, it's also limited by these two surfaces that confine the electrons. So they're not as free to move, or they recombine before they get a chance to move, however you look at it. Now this is an example of unknown new device. So this is a silicon germanium nanowire sitting on a silicon nitrogen membrane, and which has been prepared with 2 aluminum contact pads. And it's been through a heating treatment, and aluminum has diffused from the contact pads into the silicon germanium nanowire. And this is again work done by the same group, and they just submitted to publish it. So I will not show all their high resolution, very lovely images they have. I will just go through it very quickly. And in the TEM, the great advantage compared with the SEM is that you can get high resolution structural information. So we can see these 2 interfaces are not the same. You see they are different, and they have gone then into sort of high resolution analysis and decide to investigate what these interfaces are. So that's great. That's the TEM side. There's a lot of information you can be extracting from it, but it doesn't tell you anything about what this device is. It tells you its structure, but it doesn't tell you internally what are the functional parts. And you, of course, you can do an IV curve, so you can extract the current voltage behavior, and you can try and figure out what this device could be. Is it a junction? Is it not a junction? But this is an example. The IV is not very telling. It's not obvious that we have a forward or reverse bias. It's not obvious that we have a junction of sort of simple kind. However, if we turn to EBIC in the stem, and these are 2 simultaneous images, this is showing the HADAF image and this is on the EBIC image, then we see 2 spots and the EBIC signals, and these are colorized according to their current. So negative 1 or 2 nanoamps and positive 1 or 2 nanoamps. So we immediately get two different spots. So we know that's where the electric field is, and if we overlay them, we see that one is here and one is there. So both of these interfaces have a field, even though they're different in the high resolution work. And we see them, they are back to back because they have opposite signals. So in one junction, we collect electrons, in the other junction, we collect holes in this experiment. So we can immediately build a little circuit, and we have 2 junctions, they are back to back, so 2 diodes. We can add some resistance to say, okay, we have some resistance along the wire. We can say, okay, maybe we have another resistance along the surface of the nanowire, and so on. So you can build a little model, and using the IV currents, you can just start to extract parameters. What is this resistance? What is that resistance? And so on. So it links very well between the high resolution work, the device characterization work, and the electrical analysis. What is also typical of EBIC is not necessary, but it's very useful, especially if you publish to increase confidence of what you're measuring. You can do Monte Carlo simulations. We know the things of nanowire, we have the high resolution work, so we can put that into the model. We know the substrate and so on, we can add that too. And then we can put an electron beam and we can simulate as the electrons go through it. So we can see lateral displacement, we can measure energy loss and so on. And then we can also simulate induced current. So the in situ part with this device is very easy now that everything is connected and see the fields. We can easily apply whatever voltage we want. And this is just showing 2 levels of voltage. This was unbiased, so these are the built-in fields. This is minus half a volt and plus half a volt, and we can see how this field is widening because it's in reverse bias, and the other field is disappearing because it's in forward bias. This is also information that we can use about which type of doping we have inside the nanowire and so on. And if we go to the other side, positive voltage, we see the opposite. So it's a great tool also to interact with the device. And so that's kind of covering the basics. What does this whole stuff about electrical analysis means, and what are the key techniques to use? They're much more advanced, single contact EBIC, remote contact EBIC. There's also transient techniques, lock-in techniques. That's something we can talk about. So how does this equipment look like? So on the SEM, our equipment is here, so it's inside the rack. Our task is to measure this current. And it's a very small current, and we want to image, so we want to measure it very fast. So that means that standard picommeter will be 1,000 times too slow, maybe even more. So we had to build our own electronics for preamplification, 2-stage amplification, to time filters. Also had to add biasing for the in situ work and so on. So one of these units is just dealing with all this amplification, also switching which one you want to connect to high, which one you want to connect to low. And then there is another unit that deals with all the beam control, because we need to synchronize the measurement of the current with the position of the beam. So we also take control of the beam and we raster it across the sample. And then we can put all this together in the software and say, at this position in the image, we measure the half and the stem, the EBIC image, and we can say how much the EBIC current is, and so on. So for TEM, this is not a very fancy TEM. The installation is very straightforward. We just need to connect to the back of the holder to pick up this current that we want to measure, and then we have a few electronics units around as before. In terms of specifications, if you're interested in that, these are just a few headlines. Gain is a big deal, so we have to measure very small currents, and we don't really know what kind of thickness of devices you would have and what kind of induced level currents you would have. So it has a configurable preamplifier that is very wide range, so it can cope with whatever the experiment would have to. And then because of the speed that we want to go after, we also have a low pass filters and the second stage amplification. And this is typical also for picoammeters and auto zero. So you can say this is the zero current, this is the dark condition. This depends on the device that you connect to, so it has to be done for every device because every device has different RC constants. And also has various sources integrated and relays, so that you can turn on a voltage and you can change the voltage and you can limit the current, and so you don't burn the device. And then the imaging unit, in some degrees, it's very standard. It's the same as you would use for EDS or for EOS. It's a unit that generates the scan and sends the scan to the microscope and scans the beam. There's nothing particularly special about EBIC in this regard, I would say, other than we have to match the speed of scanning with the speed of the amplifier so that everything is working in synchronization. And it's also very important that we need to acquire two signals simultaneously. So that means move the beam, stop the beam, get all the signals you want, and then move the beam again, as a way of ensuring that when you overlay the images, they overlay exactly, so your field is not somehow shown in a different part of where it should be. And all the software does is brings all this together. It brings all the controls as well. And it's a microscopist kind of software, so very much focused on imaging. So big image in the middle and acquiring lots of images and saving previews and so on. And all the controls that you need cannot be automated and need to be operated, and they'll be here. So important features that we have to develop to make sure that everything works well for this technique is simultaneous acquisition. So this is an example showing two images acquired at the same time, STEM and EBIC. IV curve, integration in IV curve. So you don't have to have an additional SMU, and also you don't have to switch cables. And this is used in several aspects. In situ, as I covered, the other aspect is used to make sure that the device is alive when you start your experiment. It wasn't damaged during preparation. And another reason to use it is to monitor the reverse bias zone to see if the leakage current is increasing over time. There will be a signal of the beam damage onto the device. And that's several reasons why we had to integrate this into our electronics as well. And then we also supply an offline viewer because we have so much data put together, images with current measurements and so on. Then we also provide a viewer so you can walk away from the microscope and look at your data and extract pixel values and currents. And if you want to do analysis, quantitative analysis, and you can also use pseudo colors like you've seen throughout. So this was a walk through quite a few techniques, and I hope gives an introduction to this area. In some ways, it's quite a well-established and traditional area. Maybe only a few people in the world have done it. I would say now it's becoming easier and more popular and more accessible for everyone. So I hope I'm on time, and I believe next will be questions.